Welcome. I'm Graham Warwick. I'm the executive. It's a good start, isn't it? I'm the executive editor for technology at Aviation Week. And thank you to AAI for inviting me back to moderate. I hope I won't fall off the chair this time. So, so our panel is about R&D needs for aviation R&D needs for the future. And it occurred to me as I was sort of preparing for this is that aerospace is, as the world is in very uncertain times. Times that few of us would have predicted, you know, when we were making decisions on R&D programs and priorities 25 years ago. We wouldn't, you know, would we have predicted the supply chain challenges after COVID, the troubles at Boeing, that we have electric vertical takeoff and landing aircraft in certification. We have generative AI beginning to move into aerospace and find applications, including apparently writing scientific papers. And all the effort that is being expended, you know, particularly in Europe, on hydrogen. I mean, you know, 25 years ago, there might have been some of us that could have pointed at that, but not all of us. But of course, the aerospace world doesn't live in the here and now. Aerospace R&D world doesn't live in the here and now. It has to look that 20 to 25 years ahead so that the technologies are ready when they're needed. And they're going to be needed we're talking here about 2050, not 2025. The technologies we're going to use in 2025, we decided on decades ago. We've got to do the same decisions now with that 2025. How do you do that? How do you expect the unexpected or prepare for the uncertain? So the idea is that perhaps this panel of esteemed experts here will give us some assistance in deciding what those priorities might be and just the process of how we decide what the priorities are. So I'll introduce everybody one at a time, and then I'll ask them to do an opening statement, and I'll move on to the next one, rather than giving a long list of bios and then expecting you to remember them when we do the quiz at the end. I'll do them one at a time, and then we'll get into the Q&A. Please, questions? Use the conference IO. I have been entrusted with an iPad here, which I will completely screw up using in order to get your questions and ask them of the panel. So I'm going to start with Dr. Victoria Coleman. Victoria is CEO of Acubed, which is Airbus's Silicon Valley Innovation Center. She has 35 years of experience across multiple domains, from cybersecurity to emerging platforms. She joined Airbus in 2024, having served both as the chief scientist of the US Air Force and before that, director of the Defense Advanced Research Projects Agency. I say DARPA all the time, I forget what it stands for. So Victoria, kick us off.
Okay. Hi, everybody. Good morning. Welcome to 2025. I don't know about you all, but I'm still having a little bit of kind of Christmas kind of illness here, but we'll try and get...
Mince pies all round later, but...
Seriously, we have a lot of them left over in our house. So let's see. R&D for the next 20, 25 years. You know, one thing that I learned in my career, which is very long, as Graham kindly pointed out, not.
Shorter than mine, I promise.
Is, you know, kind of research is nothing if not, you know, an ambiguous endeavor. Like if you knew which way you're going to go, you wouldn't need research. Research is all about, you know, going down pathways that may or may not take you someplace, and having, you know, both kind of the, you know, the fortitude to pursue those avenues in times of ambiguity, and also to recognize when you've gone wrong and backtrack and start someplace else. So I don't ever believe that, if anybody tells you, you know, I foresaw the future 20 years ago, I don't know that I would believe them necessarily. You know, what I do know, though, is that we have lots of problems to solve. There are many opportunities for us to solve as a community, as an aerospace community. And, you know, what could be better than working on those problems that we know that we have today? You mentioned hydrogen a moment ago. You know, talking about big bets, that certainly is a massive big bet. Will it pay off? We don't know. Maybe, maybe not. But that's the whole essence of having, you know, the I think the optimism and the confidence to go down these pathways and explore these different things. If I were to just offer one principle, one trick, if you like, that has worked for me in my career is like, whatever you do, do it fast. Because if you do it fast and you do it at scale, you learn much faster than otherwise. As I was getting ready for this panel, I went back and looked a little bit at fly-by-wire. As you know, Airbus was the first company to introduce fly-by-wire for single-aisle jets at scale. There was a lot of discussion within inside the company. Should we do this for the A330, the A340, the wide bodies, the long-range jets, or the medium, short-range jets? And it was really interesting. If you looked at the kind of decision-making process, they decided to go with the A320. Why? Because there was a market need. So they knew that they would be able, to get that technology out there, really as quickly as possible. And they also knew that they would do so, at scale. And when you look now, kind of 30 years on, 200 million flights later, and 14,500 jets, in operation. This is how you learn whether fly-by-wire works or not. So I think working on things that matter, making sure that there is a prayer of a technology for getting after those problems. And in the case of fly-by-wire, we knew, because, for example, our friends at Lockheed had done, had built that technology for military airplanes, so we knew it could work. And if there is a sustainable business model, I don't think you can go wrong, right? So when I look at the ideas that, the people, for example, at Acubed now bring forth as suggestions, this is what I ask. Is this a problem that somebody cares about? Is there a prayer of a technical solution? And is it sustainable? If we build it and we put it out there, can it sustain itself? And if the answer is all these three things is yes, then we'll go off and we investigate, and sometimes we succeed, sometimes we don't, and then we backtrack. But I think this notion of kind of going fast, failing fast, backtracking is really essential. Musk calls this multiple rendezvous with reality. I mean, the reason why SpaceX is so successful, they can execute and all, but it's this relentless experimentation every week, flight every week. So there is so much that you can learn, and so much that you then bring to the table when you try to make a decision whether you stay, you go forth, you go backwards. Hope that was.
So thank you. So you mentioned fortitude there, and it makes me wonder. And again, I don't know whether it's changing with the way that the world is going and the pace of technology. But if you're and you have experienced this from DARPA, there was a huge sort of outward focus on DARPA's transition or lack of transition of technology that developed. If you're in a company, how do you have that appetite to do something that's riskier than others? I mean, your R&D portfolio has to be a mix, presumably, of risk, but also your paymasters, the programs and the corporation is looking at the results of the R&D and saying how many of those investments transition to. So with that fortitude, what does that mean for the environment you're in now? That how do you develop that appetite for risk or fortitude to take on risk when you're under this pressure to actually make sure the dollars deliver something?
So I think of it as ambition versus fortitude. So Airbus had an ambition to create fly-by-wire at scale. I mean, was that going to be successful? It was the first time that it was done. But there was the ambition. Now we have an ambition to automate operation of jets gate to gate. We call it G2G. At my lab, we've been working, and Amanda Simpson here that I found out just today has been helping us with this. We've got VLS, a visual landing system, now the TRL 4.1. The jet can see and it lands itself. That's our ambition. Whether we'll be able to bring it to fruition or not, remains to be seen. I'm personally very optimistic, but I think it's like setting yourself goals. It's interesting. Every company operates in a different space, but Airbus, grew in an environment that was very competitive. There were big companies out there that were already very successful, so we knew that what would differentiate us was taking risks on technology. So we've done that many, many times, and you'll see us continue doing it, for example, with hydrogen and other technologies as well as automation.
Thank you. So our next speaker is Mark Gustafson. Mark is an aerospace and defense consultant, and I won't mention how many years of experience, because apparently that doesn't go down very well.
Seriously? First rule of business, my God.
37 years. His experiences in DoD acquisition for him, technology and prototyping. Mark was most recently a Raytheon Principal Technical Fellow leading a technology development for offensive and defensive hypersonic systems. Before that, he was a DARPA program manager who was the DARPA program manager for the Hawk hypersonic air-breathing weapon concept system demonstration, which led to the HACM, Air Force HACM hypersonic weapon program. So Mark, give us your views.
Good morning, thank you. So I'm really glad to hear the thread that you guys started pulling in that last conversation, because when we talk about where we need to go in high-speed propulsion, it starts with moving faster, building lower cost systems, right? So one of the attractive features for many of our high-speed propulsion systems is the fact that they're simple, there's very few moving parts, they're expected to be manufacturable, and the fact that we can put them together rapidly and test them and fly them was the whole underpinning of the Hawk program. I expected to be flying in 5 years. Well, it took us 10 and cost us more than it should have. So there are some serious issues associated with that, and a lot of them have to do with the manufacturing and the supply chain assessment, elements of who's going to be able to put this stuff together and how they put it together, and where they build the parts and where they do the assembly. There's a lot of opportunity there that I think is low-hanging fruit. That there are other sessions in this symposium talking about additive manufacturing, other advanced manufacturing techniques. There's robotic laser welding. There's a whole lot of things that if you properly design a high-speed vehicle, you're going to make it out of conventional metals, and you can use these advanced techniques to put them together. And I think we have a great opportunity to do that. You also mentioned risk and tackling some of these problems. And sometimes, I'll say, the incentives aren't aligned as well for the large institutions to do some of these things. But if you take the time and the cost out of what it takes to do this via these manufacturing approaches, then smaller companies and innovators can start to get into the game, right? They can get in there and really start pushing up the pace. And, take the approach of Elon Musk's, I think he calls it the idiot index. I don't know if any of you are familiar with that, but the idiot index is how much does it cost to build the part versus how much does it cost to buy the raw material. And he finds the parts that idiot index is very large, and he focuses on driving that cost delta down, right, and drive that ratio down. And I don't think we've done that very effectively in high-speed systems. So I think there's a significant opportunity there. Other requirements, I think we have a flying system today that's going into production. It is, I'll call it elementary technology. If you think about the development of the turbojet, there was the Whittle engine in the West. Anyway, there was the Whittle engine. That was the X-51. And now there's effectively the GE, the original GE engine, which went into production for the P-59 Air Comet, and that's effectively the Hawk system. But we're very, very early in the capabilities that there's a lot more capability left that can be optimized in the existing systems. And I think there's really opportunities for people to build on what we've already done. That's a 50-year history of this stuff. And last, enabling that innovation that we're talking about associated with, moving faster and manufacturing these things, and smaller companies and innovators and other things that can rapidly build things, test them, and get to flight. There's a number of things that we need to be doing there. So one is we have a very long, deep history of technology development in high-speed propulsion. And we haven't done a very good job of either encapsulating that, publicizing that, or at least making it available to the people who should have this information in hand so they can go forward, and really do innovative things. And, lastly is opening up ground and flight test capabilities to the smaller companies, to the innovators, right? So, they can build small test facilities to develop RDE combustors or scramjet or ramjet combustors or any kind of, dual mode system. They can do that in their workshop. But where you start to need the integration between inlets and nozzles and combustors and put a propulsion system together, you start to get into the need for the larger integrated facilities, which are typically available at NASA and some of the other big test locations around the country. We have to do a better job of making that stuff available and making things a little bit more plug and play so that those systems can be brought there quickly. And similarly for flight test, we need to open the ranges up. We need to streamline the flight safety process. We need to maybe generate some common telemetry systems, some common flight termination devices, understand the environments they work in, make those available so that people can do what Victoria said, which is put things together, test them rapidly. Once they're ready, get them into flight very quickly. And so I think if we put all those pieces together, I think we can really increase the pace of development of some innovative high-speed propulsion systems, and that will open up new application areas, right? So things that we thought we might not be able to do, some innovator's going to come along and rapidly evolve some new capability, and all of a sudden we're going to have an air-breathing air-to-air missile, or we're going to have a reusable Mach 10 airplane, or whatever it may be. So those are my thoughts on high-speed propulsion.
So the history of US hypersonics research has broadly been a push to the customer, right? Developing push to the customer. No real pull from the customer until the last minute, and they go, give me more of that. Now that we're bringing in, the startups, the fast-moving startups, how does the customer get their head around what they can have access to? They don't understand it. They don't understand what the capability is. They don't understand how to use it until a threat presents, and all of a sudden they go, okay, now I know what I want it for. But how do you do that? How do you educate the customer when you want to move fast on the development end of things?
Well, I will say that we got Hawk over the hump with the user by showing them what the system could do. And they sent folks in to scrub us and assess whether we had it right. And when their assessors came back and said, yeah, we think it can really do that, all of a sudden the user got very interested, because what happens is he knows what his problem sets are, at least on the military side. I'm not talking about the commercial side so much, but he knows what his problem sets are. And when you bring him something that's reasonably able to accomplish that mission, is not 20 years away or 30 years away, and he sees that it's flown, or he sees that the analysis based on and that agrees with test data enables him to do something he really needs to do, he will latch onto it. The DARPA folks, the Air Force Research Lab folks, the ONR folks, they're always looking for that kind of stuff. And if they come in and say, hey, user, yes, we've evaluated this for you and we think it'll do the job, many times you do get traction and get moving forward. But that sounds like an easy case to make, but it's not.
Right. Because there's always something else competing for the money.
There's always something else out there. But if you can tailor it and rapidly demonstrate the capability the user's looking at and do it affordably, like we're talking about, low-cost manufacturing, rapid development, the case gets much stronger.
Thank you, Mark. So our next speaker is Dr. Cecilia Haskins. She is Associate Professor Emeritus for Systems Engineering at the Norwegian University of Science and Technology. Having recently retired from careers as a systems engineer and in academia, she is a consultant, author, mentor, and volunteer. Cecilia's research interests are eclectic, but focus on the application of systems thinking to societal and technological challenges. Cecilia.
Thank you very much. It's really a fantastic pleasure to be here and be with such a very fine panel of people who actually know a lot of what they're talking about in terms of what your areas of expertise are. And I'm your token sustainability person. And sustainability is a topic that we have on the tip of our tongues very, very often, maybe with less of an understanding of what that really means. And in this case, from the perspective of what y'all and what manufacturers do for a living, it's really about recognizing that we live on a planet and it has a limited set of resources. Whether they're the human resources or the mineral and other resources, they're limited. And very often we don't really think about the implications of those limitations when we try to do the original thinking and brainstorming to make new systems or create innovations. One of the other situations that I ran across, because my PhD work was trying to apply systems engineering to sustainability topics. So one of the biggest questions I had was, what are we talking about when we talk about sustainability? So I made a little picture very, very early in my process. This should work.
Oh, there we go.
Oh, this one.
That one.
Okay. So the thing is that probably everyone in the room has some familiarity with a product life cycle, starting with the processes of design and construction, and eventually the product moving into its useful life, and then eventually needing to be disposed. As systems engineers, we're very much often invited to the party in the early part of the process. And so you see on your left-hand side, you see that is where systems engineers generally have played. And then we kind of fall out of the picture for the most part unless major maintenance or upgrades need to happen. And what you hopefully, yes, I think the picture shows pretty well today. You see that there's a big heart-shaped globe, and that's our planet. And we see the planet in our business as usual minds as a cornucopia that can provide whatever we need. And then also at the same time take, as we go through our process and say, well, I do need this, but I don't need that, take also into accommodation all the waste that we may produce as part of our processes. So the cornucopia vision that is on the left-hand side is really our business as usual, which we have already recognized as being unsustainable. So sustainability means that we reduce our dependence on the planet and its limited resources, knowing and understanding that a certain amount of raw material will probably have to be virgin sourced. And as we go through all the rest of the life cycle of our product, we look at ways that we can reclaim, recycle, remanufacture, whatever the right process is, to reduce our dependency on new resources, but also protect the planet from having to absorb all of our undesirable byproducts. So this translates from a sustainable development perspective, and this is probably a wee bit of an eye chart maybe for some of you, but I'm hoping some of you are in the room because you're familiar with sustainable development and the sustainable development goals. And one of the things that's kind of very often lost when we talk in a highly engineering or technology aspect is that these goals actually cover the three pillars of sustainability, which is not just the planet, but also all of our people, and includes the prosperity. So we know that we're not running organizations to just be altruistic. So we have this understanding of the goals, and then this particular CAPSEM model, which stands for the capability of a given company to do sustainable development. So it has 4 levels, as you see. And the items that are up on the 4th level relating to change and innovation include systems engineering, material flow analysis, and industrial ecology. Now, the thing about them is they're sort of overarching principles, and they're not applied at the last minute. They actually have to be applied from day one. But then you see level 1, this is where the real processes are happening. And so we have tools out there and methods out there like input-output analysis, cleaner production, simple tools, in fact, that really even if, and this research, by the way, I should mention, was done in many third world countries. We had 2 African partners and a small country in Asia involved. And if you Google CAPSEM at any time, there's also a book that is open access, and you can get a lot more details about this model. Level 2 starts to be where now you're mature enough, you're pretty sure you've understood how to run your factory in a pretty sustainable way, and you want to start looking at, well, am I really producing a product that itself is sustainable? Am I utilizing value chains that don't violate our chance to minimize our reliability on, for example, and especially things like rare earth metals, which are so very hard because they get used and tend not to enter the recycling process. So you'll see LCA, most of you in the room have heard of life cycle analysis. It should be accompanied also, for the most part, with life cycle costing. And I just recently, as I was doing research for this, came across something called global warming potential as a brand new way of looking at the products that we're designing and making. So there's lots and lots of suggestions for methods out there. At an organizational level, there's ways that an organization can monitor its own behavior and say, yes, I'm taking care and I'm paying attention to what happens in my firm. And then, as I say, the level 4 processes have been being applied all through the whole cycles. So the only other thought that I wanted to leave you with was that I think that a lot of what is important in any industry, and yours is no exception, is that we need to see more collaboration between academia and practitioners, because there's the young engineers, the exciting people, the people you want to be there for your future. And for those of you who heard our speaker this morning, you know, to take us into, to have the leadership positions taking us into the future. They're at school right now. Those are the people you want to inspire. Those are the people you want to get on board. And you do that by having these internships and other types of techniques that allow them to get a touch and get their hands on things and feel like they're participating. So those are my prepared comments, and I'm sure I'll have more to say as the Q&A starts.
So thank you. So should we look at sustainability as a burden on engineering, something you have to do for compliance, or is it a way to get to better engineering, to get to a better product, and to get to a more competitive product if you take this systemic approach?
Exactly.
I mean, it looks like there's a potential there to get a better product, but you're never going to sell it if it's a compliance. I mean, the customer will buy it because they have to have it, but the manufacturer wants to make a better product, and they want a better engineered product. So is it a way to do that?
Yes, there is, and it's really the way a company sets its priorities. So I'm not sure how many of you in the room have heard of the term design for X, DFX, and if you put sustainability somewhere in that priority list, it becomes part of your culture. It becomes second nature to think about, well, is this really the material I have to use, or is there something else that could be used that gets the job done and is friendlier? Anticipating that I'd get some questions like this, I've recently become aware of a company making propulsion systems from recycled plastic. 2 million of these bottles is what they use per launch. So please recycle. But in any event, so there is innovation, and this is a small and just came out of the startup company cycle. So this is where even as individuals we can start to make very, very small, but they're not unhelpful. And if we put things like safety and simplicity and reliability, which are words I've heard already, in with the mix of sustainability, then what happens is you do make an affordable product, and using the newer technologies. I mean, this company is making a product that could literally not have made, what did he say, 2 or 3 years ago. It's a 3D printed high-speed propulsion for launching low Earth satellites. So there's smart people out there. We just need to get them engaged and get them helping. And yes, sustainability, they have a sustainability officer. Some people in the room might know of Aaron Blackenship, and he's the chap who keeps them, this company, on the right path. So I think it's definitely doable. They're proving it's doable.
Thank you. So our next speaker is Wendy O'Connor. Wendy is Executive Director for Advanced Air Mobility Integration at the FAA. She has come there from the FAA's Air Traffic Organization and was herself an air traffic controller earlier in her career. She's a recognized expert in change management, national airspace system modernization, and FAA budget. And Wendy most recently served as the Director of Operations Planning and Integration in the FAA's Air Traffic Services. Wendy.
Thank you. It's a pleasure to be here. Good morning. I'm honored to be up here with my other colleagues who are very smart and very innovative in our new national airspace system and the new technology coming. So it's a very exciting time in aviation right now with the movement of advanced air mobility, or AAM as we like to call it, going from a mere concept into reality. And with that transition, it calls for us to be more innovative, more collaborative, and research across multiple sectors within the FAA, the Federal Aviation Administration, which we're not sometimes very good at, but we are getting better at. It's been since the 1940s since we've had a new type of aircraft enter the national airspace system, so we're doing a lot of catch-up. But you know, it's exciting because we haven't done it in so long, and we have new workforce, and we have people starting to think outside the box within the FAA and the government sector. Since we are the regulatory and the oversight for all of this, we want to move faster, but we have the safest airspace in the world. And we want to keep the safest airspace in the world. That reputation is very important to us. We work more traffic than anyone else in the world. I think the only country second to us is Canada. And it's basically the size of our Ohio facility, as far as the traffic flow that goes through Canada. So we have a more expansive area to integrate and implement in. So we really need to focus on R&D, research and development, and we really are trying to do that in concert with looking at how to implement in today's environment into the national airspace system. But we have to use the existing infrastructure today, and we are finding that our infrastructure is not ready for full scalable operations. So we are working from a crawl, walk, run method. We're in the crawl phase. But we are looking for folks to help us understand where we have gaps and where we need to make changes in where we look from a regulatory and oversight. To your point, Cecilia, it's the young generation. We have internships in the FAA and many great young people that are coming to work for us in the internship, but also we pick them up afterwards that come up with really great, brilliant ideas on how we need to adjust. And we are willing to adjust. We just put out the SFAR, the Special Federal Aviation Regulation, which is a huge step for the FAA. We didn't put out a final one because it gives us learning room to understand how these new aircraft are going to work, and for us to gather data. We really need the data, the safety data, and that's going to take the collaboration between us and the stakeholders. So, thank you very much.
So, thank you. So, I have two kind of questions here. One is, the ones around innovation, so the FAA did create a kind of a front door. I mean, it was CC or what it was called or something. It was, I forget, the Center for Something or Innovation. So a way for pre-certification engagement and mutual sort of like, here's my idea, and the FAA saying, well, if that's your idea, here's kind of how we would, the rules that we might, and that sort of, but that was kind of a separate piece at the front there. Mm-hmm. To what extent have you been able to bring that openness or innovative thinking into the more traditional FAA departments? So, where there are decades of ways of doing things that we know are safe and processes we know are safe. How do you bring that embracing of innovation into those more traditional departments? Have you been able to do any of that?
We certainly have, and that's part of my office's job to do, is to bring those innovative thinkers in each of the different organizations to the forefront and with their leadership, because really this is where change management comes into place, right? It's top down and bottom up. With change management, so it gets the middle and everybody's working together and thinking outside the box. So in each particular organization within the FAA, and we have lots of them, by the way, so it makes my job very hard to herd the cats, basically. But we're doing it. We have people really, really looking at, okay, we did it this way, but it may work better this way. So maybe we need to think about it in this realm with this particular rule, or we need to change those rules. I have the air traffic organization thinking outside the box of, well, this is a new aircraft, how's it going to mix with the regular air traffic? Now they're thinking, oh wait, I think we can do this here. How does this work?
Yeah.
And we've set up, we'll get more in discussion on kind of what we're doing in the R&D and research that we're doing to help change those mindsets.
So I want to just make a personal comment here, because you mentioned the SFAR, and I remember when the draft SFAR came out, it was very traditional FAA. It was like, they've taken every email that had gone around inside the FAA saying, you can't do that because we've never done that, and they just stuck it together into this giant document that was a bunch of people's opinions saying, you don't go and do that, no. Then the final SFAR came out, and industry said, wow, it didn't give them everything what they wanted, but every single piece is argued. They said the way that the FAA has explained its reasoning for why they got to that point, and the fact that they inserted these options for other ways of doing it, the two are night and day.
Yes.
And I mean, and I think the final SFAR is a really interesting example of how the FAA can do regulation.
Yes.
And it was done within the we never thought the FAA would do it in the time allotted, but it was done, and generally regarded as a good piece of regulation. So.
We did it, yes. Yep.
So I have another question too about continuous experimentation and R&D, but we'll come back to that one. So our final speaker is John Whittenbury. John is Senior Director for... I love this title, by the way. Senior Director, I don't know whether it's a typo. Senior Director for Aircraft Advanced Design and Research and Advanced Design at Northrop Grumman Aeronautics Systems. He loves advanced design so much, he has it twice in his job title. It may be a typo. I'm not going to mention how long he's been in the aerospace industry, but you can kind of see a trend.
High will go low, right?
His career has been an engineer, chief engineer, program director, including working not only for Northrop, but for Lockheed Martin, Skunk Works, and for NASA. And he was inducted as an AIAA Associate Fellow for the class of 2024, which is, congratulations. So it's not indicted. John, please, sorry, go ahead.
Well, thank you. Good morning, Greg. And, good morning to you and to my fellow panelists, and also to our Forum 360 attendees today. It's a pleasure and privilege to be here today to be with you. And I do serve as the Director for Aircraft Advanced Design within our Research and Advanced Design division.
Okay, right.
So just to clarify that. One exciting theme for our SciTech this year, energize the future. And as I think about that and reflect on what does that mean for aviation R&D requirements I had a few observations that really build upon what my fellow panelists have discussed this morning. And these are my personal observations. They do not reflect official Northrop Grumman positions, so just to make sure that's understood. But as we look at things like how do we accelerate product development, I like to look back in history to see how did we do it before. Look at the Spirit of St. Louis. Went from contract award to delivery in 60 days. The P-51 Mustang went from contract award to first flight in 102 days. And then you look at the A-12, the predecessor of the SR-71, going from full go-ahead to Mach 3 flight in just a little over 3.5 years. Just amazing. How can we recapture that? What can we do, especially given the fact we have tools today that are so much more capable beyond slide rules, Freedom calculators, IBM 360 mainframe computers. And I think the key there is the digital ecosystem that enables us to do requirements analysis, trade studies, virtual prototyping, right up front where we can do it most efficiently and have the least impact to the overall program. Mm-hmm. And to build on what Dr. Haskins said, taking a much broader system level view. Typically we like to draw the system boundary around the air vehicle. And maybe it includes a control station, and maybe it includes a supportability segment. We need to draw that system boundary much broader to include everything that goes into that. Where am I getting the raw materials? How am I processing them? Where am I getting the fuel? How do I make that fuel? And then thinking through the entire system life cycle in terms of not just system performance and cost, which is extremely important, but reliability, maintainability, supportability, through sustainment and disposal, and think through that entire process. And that's where we can leverage the digital tool set to do that, the digital ecosystem, to work through those different trades. Yeah. And then how can we collaborate with other industries as part of that? So automotive is one thing that comes to mind. Looking in the past, the automotive industry collaborated very well with the aircraft industry during World War II, producing thousands of aircraft. Now today, the scales are very different. However, what can we learn from that in terms of design to manufacture, for manufacture? Unitized construction, reducing part count, first time quality assembly and fit, determinate assembly. How can we build things much more rapidly, particularly if we want to build things at scale, mass produce at scale? So how can we leverage that? So that's just one example of collaboration there in the industry. And I do think that there's tremendous opportunity within R&D to do that. And again, taking that system level view so that we think about the ramifications across the product life cycle. And that will also help us develop systems that are much more robust and safer. I think we should also make sure that airworthiness and safety is baked in from inception and design, and is a natural part of the design process, so it's not an afterthought. And so that as we develop the product, we can collect the digital artifacts in that one set of information that we share with our customers, our industry teammates, to make sure we're all working off the same sheet of music. And that's where I think it's going to be very important to make sure, again, within that digital ecosystem, that we have standards in place, modeling standards, interface controls, to make sure that we're all working to the same levels of rigor to build that digital ecosystem product so that it can live and be maintained through the entire product life cycle. So I think there's a lot of exciting opportunities within R&D, and again, I'm very pleased to be part of this panel today and honored as part of my fellow panelists. Thank you.
So thank you. Expanding the boundary, again, it goes kind of to what Cecilia is talking about, bringing the sustainability factors in. Where are we in engineers need design tools, right? We don't use, well, we try not to use pencil and paper and that sort of thing. We need design tools. We need things we can click on, icons we can click on that will then do the good job. If you're now talking about moving out of the design box that you've drawn around an air vehicle or a weapon system or any kind of a system, and you're now saying, I want to bring in raw material supply, I want to bring in sustainability, I want to bring in all these things like that. I want to bring in collaboration with an industry that's not anything to do with aerospace because they know what they do. The tool development becomes key to that. because you can't do that manually. You're going to have to somehow, and you say integrate them, you're going to have to share data. I mean, so does R&D, does that become an increasing piece of what the R&D puzzle is that you, not only do you have to prove the thing to TRL, whatever, but you've got to have the process, the tool, the whatever it is that enables that to be used. That's got to come out of the R&D process as well.
Yeah, Graham, I absolutely agree. And I think tool development is something that has to be a continuous effort because tools are typically based on a lot of empirical data, and that empirical data set will grow, obsolete as technology moves forward, and we need to continually refresh those tools and also expand their boundaries. And so it means working with other industries to understand what tools are you using to expand that system boundary and understand the ramifications to the overall system design. And then expand the tool set to include, at a conceptual level too, what are the first order effects that we need to consider? For example, fuels. If I'm considering alternate fuel sources, what are the ramifications for production, support worldwide, storage? What are the combustion products? What are the disposal concerns? Thinking through all of that process. But I do think that tool development is something that's a continuous process, and that if we're using tools that are based on empirical data, then we have to continue to look at the basis of that data because it's going to provide similar answers. How do we take that further forward beyond the current state of the art and look forward to the future?
Thank you. So we're going to move to the Q&A. I'm going to ask a couple of my own first, but then we'll move to... I want to tackle this we need to move faster thing, because I actually don't believe it, right? And the reason I don't believe it is that the customer has a time constant. The customer has, if he's an airline, they want to buy an airplane, they want to operate for 15 years and get their return on investment, and then they want to change their fleet. They don't. It takes that long for an airline to get its money back off an airplane. The customer, the military customer, has a time constant. They have a fleet renewal time constant, they have a budget time constant, they have a planning time constant, they have a whatever. If we move fast, you just create gaps. Or you need to somehow anticipate when to put your foot on the accelerator so you arrive at the destination when they need it. We're looking at in commercial aviation, neither an Airbus or Boeing are rushing to launch a new airplane at the moment because they've got backlogs that they can't build because of other issues. They know the customer, and the customers are getting quite vocal about the fact they want an airplane, but there's a business to be run. So I wanted to begin by saying, where do we apply the speed? Where is it valuable to apply speed? And where does it make no sense because the customer's not going to be ready when we're ready?
I think that's a great question, and maybe I can just foot stomp a little bit with what you said. I think hypersonics is like the poster child for this. I was at DARPA when we were doing some of our runs on the TBG, the tactical boost glide vehicle. We flew once every 6 months. And if you looked at the kind of question payload, if you like, that every one of those tests had to go answer, was out of this world in terms of complexity. So, if you fly once every 6 months, it's going to take you, a century to get there. If you fly once a week, you will learn so much faster, and you will fail so much faster, and then you'll be able to go back and fix things. So I think as we develop new technologies, in order to learn fast, you have to try things fast. I mean, you don't learn fast by sitting and imagining what the flight test would be like. You need to be out there in the B-52 at Edwards, and seeing what happens. And I'll tell you, the other thing that is remarkable when it comes to hypersonics, and just parenthetically, we touched a little bit on manufacturing and how important that is. When you go into an R&D lab, get an R&D job, the first thing that you think about, I'm going to build this amazing new thing that's going to do things that nobody's done before. And that's true, we need to do that. But we forget that manufacturing in and of itself is an endeavor that requires R&D, especially for it, right? And so I'll tell you, like with the TBG, for example, we couldn't get the boosters to fire. And I remember sitting at DARPA and thinking, how is this possible? In the year of our Lord 2020, whatever it was, we couldn't get boosters to fire. These are very, very important things that we kind of tend to discount because It's just firing up the booster. Well, it's not that simple, turns out. So I think having kind of respect for the complexity of the manufacturing process as an endeavor that in and of itself requires R&D is a very important piece. And back to the speed, when you're learning, you need to learn fast. Learning slow is a fool's game.
So is there a point, is there an inflection point in the process towards a program where you need to get the learning and you say, okay, now I can slow down, now I've got the learning and I can then go at the pace the customer goes at? Or do you have to maintain that pace?
So you know, in the Department of Defense, we have this RDT&E phase where we develop things, and then we have the production phase. I think you never slow down. You just run faster in different areas, right?
Yeah. Because one of the questions we got here about is the valley of death, and it seems to me if you run fast at the beginning, you just hit the valley of death quicker because the customer's not ready, or the customer hasn't heard about it yet or something. I don't know. I mean, or can you does moving fast get you across the valley of death more quickly?
So to respond to that, Graham, let me ask you a question. So what do you think came first? An Air Force requirement for unmanned wingmen, or the flight of things like Boeing's unmanned vehicle and X-58 and other things like that? I mean, the technology had to be proven to a certain point before somebody like Secretary Kendall would roll in and go, why aren't we doing this, right? And so there is a bit of chicken or egg problem here, and I will grant you that if we'd have flown 50 different unmanned combat vehicles before the Air Force adopted a requirement, once it got into the system, it's still going to move at the pace of government. But at least it got into the system, right? So you can argue, well, what do we do about the government system? That's a whole nother conversation, right? And I don't think anyone in this room wants to tackle that one. But you've got to accelerate the pace of innovation that of the things that we can do. And as new needs start to emerge from a conflict or from a projected military capability need, that industry and innovators can rapidly bring those new things to the table so that the military process can adopt them and get moving.
Yeah, because Valley of Death is really about the cycle of adoption. And you can have a Valley of Death, but what every industry needs are those visionaries that are willing to take that risk, no matter. They are working, this small company I mentioned before, they're working on technology that's been in the vision of people for 80 years. And it's only just now that the technology has caught up to a point that a risk non-adverse company can say, yeah, this has been on the drawing board for a long time. Now we have some ideas about how we can do it, find some investors. And as I said, the company that I'm referring to has just moved out of the prayer cycle into a position where they can do demonstrations that prove that there's something there. So I think the other analogy that works for Valley of Death is Field of Dreams. And again, if you're risk adverse, you kind of just believe if you build it, someone will eventually buy it. And at least it's paid off for this company. And I think you really have to find those visionaries out there and hope that they have the courage to take things forward. But they have to move fast, the constant, continuous innovation to make something that's never existed before better and good enough that it could be adopted by someone else.
So when you're on the government side, you're on the receiving end of speed if we achieve it. What's your
Yeah, you're going to have to
approach to that? I mean, how do you view, if we can move faster as an industry, what does that mean for you as a regulator?
We don't necessarily want you to move faster.
And there you have it.
We will not be able to get to, some of the scalable operations that some of the industry folks are talking about because we're not ready in the airspace. To your point, and so the community's not ready for it yet. A lot of them are not aware of these new entrant vehicles. I've talked a lot with the public, and they just had no idea. They are thinking conventional takeoff and landing aircraft, your commercial airliners. So to them, this is new, and for some people in our period, this is like the Jetsons come into play. So that's how far it's taking us and so forth. So we want to be able to gather the data, the safety data, which is very crucial for us, which goes back to the risk base that Cecilia's talking about, that helps us get that community buy-in and the public buy-in. If we're working with industry folks closely, which we are, and we're gathering the safety data from those real flights without people on board, because right now we're only working on piloted and remote piloted aircraft. We're not even getting into the autonomy world, which is way further down the road. So once we get community and public buy-in from remote piloted and piloted vehicles, in concert we'll be working towards the very, very far off future. But I think once we get that, I think it'll be really, really good. And then we'll be able to have time to understand what we need for the infrastructure, for that integration and implementation from a regulatory oversight perspective.
So Victoria talked about this continual experimentation, which is SpaceX. And that's what's always amazed me is they all fly and experiment on operational launch. NASA would never mix the two. So therefore, you just don't get that learning because, SpaceX is launching, 10 times a day or something like that. You know what I mean? And everyone is carrying a little piece that wasn't on the previous one because they wanted to get the experience. Now, the FAA is not kind of like, not well known for R&D. It's not a big, it's not, I don't get a lot of money for R&D. But where you have done experimentation, it's had good results. I mean, IPP, yes. Beyond, I think the Keysight that's going on now with the drone delivery. Is that something you need to do more of, be able to do more of?
I think it is, in this particular realm, I think it is something we need to do more of. And we are working towards that. We are working towards setting up several key sites across the United States to work with some of the industry folks that are prepared to bring their aircraft in for us to interact with it, understand, start gathering data from it, so we can inform our safety analysis process, which would be part of the R&D. We've also have CRADA's collaborative research and development agreements with several of the industry folks, which is helping us learn at the same time working towards an integration and implementation, but seeing what that bigger picture is going to look like. Because just like you mentioned, it's not just advanced air mobility that needs to be integrated in the airspace. We have UASs that we've integrated. We have commercial space that we're trying to reconcile with the commercial airliner paths and so forth as well. And our commercial airspace launches are becoming very, very frequent, more and more. We increased, I think, like 100% this year, or last year alone. We're in the new year. Happy holidays to us.
John, I want to ask you, you can answer any way you want, but I had a very specific one I wanted to ask you because of the way that Northrop is structured. Does it help with velocity, crossing valleys of death, getting the customer to understand, if you are a company that is working across manned, unmanned platforms, weapons, and that you can reuse technologies, or if you do it somewhere, it can be applied somewhere else? Does that help, and does it a challenge for the company to get its head around how it can use what it's developing?
Yes.
Yeah, Graham, that's a good question. And in fact, we're continually looking at, reuse of technology where appropriate and applicable, and then where do we need to go beyond to reduce the risk, increase the technology readiness levels, integration readiness levels, manufacturing readiness levels of technologies that are not quite there yet. I think that's where it's so important to work in partnership with our government or commercial customers, right? To make sure that we understand what their speed to capability timeline is, and then work together to establish a set of milestones that are more knowledge points in terms of a calculated risk that we can work together collaboratively to define that will mature those technologies to the necessary levels. And this goes back to where the digital ecosystem comes in, because we can help bridge that valley of death by doing a lot of requirements validation, verification up front as part of that digital tool set that we share completely openly with our counterparts to make sure that we're all looking at the same source of truth, right? The artifacts are there. We can collect the digital artifacts that can then provide that traceability.
Yep.
But to answer your question, we do continue looking at reuse of technology, but then also making sure we take both a strategic view to see, what are the things we should be working on in industry long-term for those next generation technologies, and then a tactical view on what things need to be matured right now in order to support a product timeline.
So for the regulator, yes, reuse of technology or standardization is very helpful for us, especially when it comes to certification. We have so many of these new types of aircraft that are very different from each other, whereas we've had, in the conventional takeoff and landing aircraft, we've had basically a standardized, but with just slight nuances. And so that's helped us do certification a little bit faster and understand from a flight standards operational perspective on how they need to operate in the airspace. So that does help us.
Yeah.
Yes.
I wanted to, as an ancillary to the speed, I wanted to do the fail fast, fail often thing, which I also don't believe in. But so Acubed was formed with one of the reasons behind Acubed was to try and bring the Silicon Valley culture into Airbus, right? Has there been any change within Airbus proper, and that's not the right word, but within Airbus as a result of exposure to that fail fast, fail often, risk acceptance type of culture? Has it opened the aperture within Airbus to do that at all?
Yes, I think it has. I think all organizations go through, development, learning. I think Acubed was an amazing experiment that started in 2016. It started as a disruptor, and I think it had to be that in 2016 because there was no way to do. What Tom Wenders was trying to do was to show the difference between how the world outside was doing things and how Airbus internally was doing things. So to do that, he really had to highlight the differences and the different way of working. The first thing that Acubed did, as you probably all know, was Vahana. So the first ever eVTOL for Airbus. This is 9 years ago. So today it's kind of commonplace, perhaps 9 years ago, not so much. So clearly, the ways of the valley, the ways of the valley, which includes talent, it includes technologies, but also best practices. These are the things that can let you move fast, and these are things that we are internalizing across the board in the company. So it's not just about, I made a new gadget. It's like, how did you work, and can I learn from that so that I continue kind of expanding my capabilities. I'll tell you today, and this was one of the challenges that was offered to me, if you like, as I went into the position. Are you still a disruptor? What have you done for me lately? All of you here who work in R&D labs will have to answer that question. And as I took a look around and saw what we were doing, actually, what the lab is doing today is accelerating the company. We're not disrupting because, if I'm sitting, someplace trying to build lots of, deliver 800 jets and not quite making it, having you come and disrupt me is not what I want to hear. Just to be obvious. So we went, we went from this life cycle from being the disruptor to being the accelerator. And I think that's the right place for us to be. I do believe it's making a difference. And again, Airbus is a company that is not afraid of technical ambition. So Acubed is, I think, it's the tip of the spear when it comes to that.
John, I want to ask specific with Northrop, do you have examples of where you've been able to successfully accelerate something? And do you know, what was the things that made it work?
Well, a good example is the work we did on the X-47 program, back in the late 90s, early 2000s. We made a conscious decision to build a demonstrator, the X-47A, to give us the experience and the capability to go forward for a naval unmanned combat air vehicle, for example. That was done very rapidly, and then that led directly into the X-47B program, which was able to demonstrate autonomous carrier launch and recovery off of an aircraft carrier and airspace operations. That was over a decade ago now, as well as autonomous aerial refueling using the Navy-style method. So those are some examples of rapid product development, and certainly working with our scaled composites team, which do very rapid product development for various applications.
Mark, when you were doing Hawk, fail fast, fail often thing, which is kind of built into DARPA's thinking, that. But if you fail, you get an investigation. If you get an investigation, it's months before you get back in the air again. And so when you're doing a program like that, did you try to find some way to accelerate that process, knowing that, we're going to fly these and they're not going to work? Can we at least get through the paperwork and fly again?
So in fact, Hawk was a joint DARPA Air Force program. DARPA was leading it, but one of the reasons DARPA was leading it was because DARPA does their own airworthiness and investigations for failures. And the Air Force system can often be slower and more cumbersome. We had to do a conscious trade-off early in the program about whether to build less capable, smaller, but significant steps in vehicle evolution and flight test, or should we build basically a replica of the full-up thing? And it was decided that people wouldn't necessarily believe that this was a real capable system unless we went to a large-scale, effectively a full-scale demonstration. And so that's what we did, but with that came, we got to, no kidding, build the whole thing, right? And so that slows you down because you have to build a larger piece of hardware. It has to have more capability. It has to fly longer. It has to go on a test range that can support longer flight tests, which limits the number of platforms you can launch off. I mean, there's a whole waterfall of things that go along with making that decision. But we did very consciously think about how could we speed up the cycle of learning. And unfortunately, I shouldn't say unfortunately, but I mean, it didn't go as fast as we would have liked because of that.
I want to go and ask Wendy, Wendy, the regulator, how do you fail fast, fail often? If I come to you with design for certification and I say, just don't look at the runway behind me because there's a whole bunch of things, smoking heap, get here. I mean, do you have to take into account how they get there? Or do you say, no, you've come to me with a design that's for certification. I don't care how you got to that certification design. Because that way I can go off and do whatever I want back here and not worry about what you guys might take into account. I don't know. I mean, how does the fail fast thing play?
So not necessarily. They take the certification design, they take a look at it. This is really not my expertise, by the way, but from what I understand from the air certification organization is they take the final design, and usually it's an in-depth ConOps. So there probably is a little bit of how they got there in the concept.
Right.
With the design that they've come up with. And then they'll follow up with multiple questions a lot of times, especially if it's a new type of aircraft, right? So that's basically how they've been doing the process. And they look for the final design, of course, and some are not done with their design. So it's a follow-up. It's a constant follow-up, which slows the certification process down.
So we're sort of covering the questions here sort of indirectly as we go around here, but there's a question here which says, if our tools are so much better and faster, why is innovation slower? Are we overthinking the solutions? I want to just add to that. One of the traps I think the industry is falling into is the tools are so good. We are getting to a preliminary design level of fidelity in the conceptual design phase. And that does two things. One is you've closed your options off early, so you may not have the best design because you didn't spend. Secondly, you're doing it to impress the investor because they look at those CAD drawings and they say, oh, look, that's where the coffee cup goes, right? So you guys are ready to go. I mean, are the tools, the question is asking is why, if the tools are so good, are we still moving too slowly? Is there an answer there? If the tools are not everything, or are the tools actually making a difference?
I think you have to look at the applicability of the tools and know when it is time to actually build and fly. And going back in the past in history, the tools did not get you all the way. There came a point where you reached the limits of analysis and you had to build test articles. A12SR71 is a great example of that. And then you're able to use those results to inform the design database going forward. There is a danger of that analysis paralysis if you continue, over-optimize. There's a point where you do need to break loose and pull the pencils away and build hardware and test and test rapidly and get into that cycle, because then you're able to validate the tools, which is equally as important and extremely important, obviously, to go forward.
What do you think, Dr. Beck, what do you think is going to be the impact of AI on testing? I mean, will it speed testing up?
So generative design with AI is very interesting, and it's an area that I think is fascinating. How can we leverage that as a tool, used responsibly and with a person on the loop, right, to help inform that design of experiments, if you will. Very powerful tool. We're just now really understanding how the power of that, but it's definitely here. Question is, how can we use it as another tool in the toolbox to help explore that design space rapidly? And it may provide some very unusual conclusions that we may not have thought of before.
Yeah.
Cecilia?
And it'll be related to what John's just said, but even in the world of sustainability, we talk about life cycle analysis, but we are really also extremely deficient in the material data that is actually needed, and I'm not even sure if engineers here who are designing for the aerospace industry actually are able to get access to data that has not yet been made available to the tools. And so, yeah, tool growth, tool maturity, I think, John, you alluded to this, I think it's going to be a really important area of actually expertise moving forward into the future, because if we are going to have tools that we can rely on, we're going to have the time to validate them, and the time to build them up in a responsible way.
Yeah, so the way I look at the usefulness of these design tools is really, it's about confidence, right? It's about confidence that your design is going to do what it needs to do and is put into the right environment. And there's multiple ways to get there. One is to develop better analytical tools that, theoretically you believe can accurately predict what some design is going to do. But to his point earlier, the A-12 didn't have very many good design tools or very many good test facilities to test out what that thing was going to do before they went and flew it. And yet, they were able to rapidly put that thing together and get it into flight very successfully. Well, how did they do that? Because the way they did it was through experience of their engineers. Their engineers had been through dozens of airplane developments, right? You'd look at Kelly Johnson and his team, they went all the way back to the XP-38. I mean, those guys had confidence in what they were doing through rapid iterations and many, many cycles of the engineering process. They didn't have all those tools. They didn't have the ground test capability, but they did have the experience. So there's some blend of experience and tools that goes together here at the end of the day to develop the confidence to enable you to go successfully fly something. And I think we shouldn't forget the fact that moving fast gets you experience and confidence very quickly.
All right. Yeah. So we could go on for ages, we're running it out. I think I'm just, rather than introduce a new topic, I think I will give the audience 30 seconds back. That's a sip of coffee, I think. So I want to just thank my panel, thank AIAA for organizing this, and thank my excellent panel here. So Victoria, Mark, Cecilia, Wendy, John. I ran out of fingers there. So thank you very much, guys. Yeah, great conversation. Give them all a round of applause, please.
Yeah, thank you.